The last one I'm going to take a look at tonight is that bonus problem from the homework. And it really shouldn't even be listed as a bonus because you all know how to do this. I always start by writing down the information. How many molecules, so kind of think about what we're looking for here, are there in 985 milliliters of nitrogen gas, which we know nitrogen's diatomic, so N2, at 0 degrees Celsius and a pressure of 1.00 times 10 to the negative 6 millimeters of mercury. Right off the bat, we see that we have a volume, we have a temperature, and we have a pressure, and we see number of molecules. When we see that word molecules, we should be thinking about Avogadro's number, 6.022 times 10 to the 23rd. And then what can we relate that to? We know that we can relate that to 1 mole. And so once again, if we use the ideal gas law, pressure times volume equals N, which is moles, times the universal gas constant times T, we can solve for N and then take number of moles and convert it into molecules, which is exactly what we're going to do. But we've also got some conversions that need to take place before we ever do that. First thing, remember that universal gas constant is based on liters. So let's go ahead and turn 985 liters into, 985 milliliters into liters. And to do that, we're just going to move our decimal 3 places to the left. So we have 0.985 liters. Let's get rid just a little bit. Our temperature is currently in degrees Celsius, and we know that, again, that universal gas constant is based on Kelvin, so we're going to change that into 273 Kelvin. And last but not least is our pressure. We can go to ATM or kPa. Why did I put a P up here? That should be a V. So let's go to kPa this time just to do something different. We've got that 1.00 times 10 to the negative 6, and again, that's millimeters of mercury. Think about that barometer. And we want to convert that into kPa. We know that 101.3 kPa is the same thing as 760 millimeters of mercury. Remember, anytime you're putting something that's in scientific notation in your calculator, please put it in parentheses. Save yourself the headache. And I'm getting that new pressure is going to be 1.33 times 10 to the negative 7. And again, that's in kilopascals. Just kind of change it up a little bit. Now, let's take all of this information and plug it in to our original formula. So pressure 1.33 times 10 to the negative 7. And again, that's in kPa. Times our volume is 0.985. That's in liters. We're trying to solve for N, which is moles. We're going to use 8.31 this time as our gas constant because of that pressure being in kPa. And from here, once again, it's an algebra problem, and this is where you've got to be very careful that you're putting it in your calculator correctly, because if you're not, you're going to get the incorrect answer. And all that work would be for nothing, which would be really frustrating. And number of moles, this is actually a very small value, 5.77 times 10 to the negative 11th. And again, that is moles. Okay, so we know that if we have that many and we want to convert that, and that's in moles, we're trying to convert this into molecules. We know that 1 mole represents 6.022 times 10 to the 23rd molecules. And so let's see how many we have there. And it would look like we have 3.48 times 10 to the 13 molecules if those were the given conditions and the given values. Okay, so again, that PV equals nRT, that ideal gas law, is very useful when we're looking for masses, moles, or number of molecules.